Okay, we're going to start in just a minute with a brown bag session focusing on the Singularity project out of MSR and its uses in enabling academic research. I don't know if many of you noticed coming in, but on the chairs by the two doors, there's a copy of a paper that was written by Galen Hunt here and Jim Leiris that is an overview of Singularity and the thinking that has gone into the project and has informed the choices that the Singularity project has made in building Singularity. So I want to encourage you all to grab that, if at least on your way out, or if you're more interested, grab a copy now. Ding means it's time to start. So our format is I've asked Galen to come and join us and give a quick overview of Singularity, both as a project and as an implementation and as a research project. And then I want to follow that with a few comments about what we're doing together to make Singularity available to you for your research work. So let me introduce Galen. Galen is principal researcher in MSR's operating systems group, and with Jim Leiris co-leads the MSR Singularity project. He joined MSR in 1997, where he stayed except for a 2.5-year sabbatical in the Windows Server division. Galen's more successful efforts include writing the Detours package and the first prototype of Windows Media Player and its networking protocols. Galen has asked me to include in his biography that he's contributed numerous bugs to numerous Microsoft products over his years here. I think also has contributed numerous bugs and significant contributions to a variety of open source projects over his career as well. Galen holds a PhD in computer science from the University of Rochester and has been awarded 31 patents.
Thank you, Mark. Thanks, Mark.
Yeah.
And I saw Michael Scott was here in the audience. He's my advisor. I think he might be here to revoke my PhD, so we'll see how quickly we can get through all this. I wanted to give a nutshell, Singularity in kind of a nutshell. I think probably most of you at least have heard of the Singularity system. Singularity was a research project Jim and I started about 3.5 years ago in how do we build dependable software systems. Thinking, if you started completely greenfield over from scratch, how would you build more dependable software systems? And our primary laboratory for doing that is this operating system that we've built from scratch called Singularity. It's a research operating system. It's not intended to ever be a product. It was never intended to be a replacement for Windows, but instead a test bed where we could try out new ideas. The goal of the system was to overcome as many faults and limits in current operating systems as we could, particularly trying to drastically improve both the dependability and the security of the system, and achieve good enough performance, but performance was definitely not a primary criterion. And within Singularity, we really had 3 core ideas that we've used to drive our research. One of them is building the system entirely out of safe languages. So when I say safe, I mean memory safe and type safe. So languages like C#, for example. Another one is the idea of using verification tools. In particular, Jim's team, for the 10 years before we started Singularity, his team's been working on static verification tools, trying to eliminate as many of those bugs that I write. And then the final idea is improving the underlying OS architecture to allow better use of verification tools and better use of safe languages. And I'm not here to say that there's any one magic bullet. I'm here to say, I guess in a sense, there's 3 magic bullets. That if you use safe languages and verification tools, that allows you to improve the OS architecture. The improvements in the OS architecture have this beautiful reinforcing property that they then make it easier to verify additional properties in the system. And that's really the core idea behind Singularity. The architecture itself is founded, again, as I mentioned, on static verification. And there's 3 core contributions in the architecture. The first one is this idea we call software isolated processes. So a mechanism for isolating pieces of code, programs, processes from each other using static verification instead of hardware protection mechanisms. Next one is contract-based channels for verifiable communication between processes. And the final is manifest-based programs, and the idea of actually having a way of describing what a program is to the operating system so that we can reason about what an individual program looks like, but moreover, what a composition of programs into a system looks like. And I'll drill down on each of these in a little bit of detail. So the first one is a software isolated process. And the first thing I want to say is, well, remember everything you learned in OS 101 about what a process is. A process is a set of code and data pages. In Singularity, a software isolated process is very similar. It's a set of code and data pages. Where we diverge is that the data pages have to contain typed objects. And so we have to be able to look at, we demand that we can look at any byte in any data page and figure out exactly which object it belongs to and what its type is. Okay? The second property where we vary is that code pages have to contain safe code. And so we have to be able to read the code and verify that it's both type safe and memory safe. Okay? And because of this, we can still have processes that are a set of pages. It's very easy to clean them up because we just go collect their pages, things like that. But we don't need hardware protection to isolate the processes. And this allows us to implement very, very cheap, very lightweight processes. The processes have some additional properties. There's no shared memory between processes. All of the communication has to take place via message passing over a transport mechanism that we call a channel. For concurrency, we have lightweight threads. There's a very small ABI, an application binary interface, between the SIPs and the kernel that has some nice properties. And finally, we seal all of the processes at execution time. So before you start a program, you through the manifests, label which code is going to run within that process, and then as soon as you begin execution, the code cannot be changed underneath. And that allows us to do provides us some very nice benefits in terms of what we can statically verify for analysis, but also for security as well. So communication between SIPs takes place over what we call a contract-based channel. Okay, and a channel is you can think of it, it's very similar to, say, a mock port or in other words, message pass system. It's a mechanism that says, here's how two processes communicate. Here's the transport between two processes. But channels have a contract, and you can think of a contract as a description, a static language expressible static description of the types of messages that are allowed to pass between two processes using this contract, and also the allowed ordering of messages within that communication. Okay, and I have here a very short snippet taken out of the TCP connection contract. So this is the contract describing a TCP socket between a client, in other words, a process, and the server of the TCP, in other words, the TCP/IP stack. Okay, and what I don't have any of the messages here, but what I have is a very short subset of the state machine describing the communication across that contract. So we have a connected state. Once the socket's in the connected state, I can, as a client, I can read data from the socket, and I can write data to the socket. Okay, and when I read data from the socket, when I issue a request to the TCP/IP stack asking to read data from the socket, that puts me into the channel communication into a reading state, and the TCP/IP stack can reply with one of three possible messages. It can send back the data message saying that there's data available, here it is. It can send back a no more data message that tells me that we're actually in a send-only mode, and so I can only send until there's data available. Or it can send me a remote close message that tells me that the other end of the the other end of my TCP session has closed, and so I won't be able to send any more data to that party. Using the contract, we can create some first-class language constructs for sending and receiving messages across this channel for IPC. And so I have a snippet here of some client code. So this is a program that is using the TCP stack to send and receive data. Okay, and so it sends a read request to the in order to pull data out of the TCP stack. It sends a read request to the TCP stack, and then it checks to see if there's data. If there's data coming out of the stack, it puts it into a buffer. And if the other end of the stack has been closed, or of the TCP socket has been closed, then it closes out the session and exits out. This particular snippet of code came out of our HTTP server in Singularity. And we had, one of the things I should mention is we had the implementation of channels and contracts and the system up and running for about a year before the verifier came online. So this is, and the great thing about these channels is we can verify the communication. So when the verifier came online, it popped up a message and said, you didn't handle the no more data case on this particular, this particular point in the code. Okay? And so what this is, the verification property of these contracts allows us to do is to detect some very subtle developer errors in the code statically at compile time, and then we can fix them very, very quickly instead of having to expose them over long periods of time in a data center. In fact, in this case, this error in our HTTP server had been there roughly about a year. We'd never realized the error was there. I'm sure we'd seen problems in the lab, but the static verifier picked it up in under a minute that there was this error there. Okay, so it's a very, very powerful feature. This was the day the engineers on the project quit complaining about the contracts and how hard they were to use. Third idea, of course, is these manifest-based programs. And what manifests allow, the way I should describe this, in a traditional operating system, say Linux or Windows, a program is, well, in a Linux-type world, it's an A.out binary. In Windows, it's a PE executable. It's a bucket of bits, and you just give it to the operating system and said, hey, point the program pointer at this entry point and try to execute these instructions. In Singularity, a program is defined by a manifest. And there's a very formal process of how you introduce a program into the system. And the manifest declares both the requirements that program has in order to execute and also the services that it provides to other pieces of the system. And I have a little snippet of code for a manifest for a device driver in this system to show an example. So this device driver, when the programmer writes the device driver, they can say, hey, I need a PCI device with the 8811 signature on the end of it. And you can also say, well, I need a frame buffer. The hardware needs to provide a frame buffer that must be at least 4 megabytes in size. And so you can specify what the hardware resource requirements are, but also what the higher level abstract requirements are. For example, the device driver says that it must have a channel connecting it to the I/O manager that provides it services there. And it also publishes the services that it provides. So in this case, the driver is saying, I provide the video capability to the rest of the service. Okay? And with this manifest, well, we can check when we install the program and make sure that all of its requirements are met. So for example, we can verify that two drivers aren't going to conflict over the use of hardware because we can read the manifest and analyze them. We can also I'll tell you, there's something else we can do. I can't remember what it is. What? Yeah, Michael's reminding me because one of his graduate students came and helped on this project. We can also check things like load order. We can also check the entire system and say, do we have a video capability? Okay. One of the other things we can do is we can use this for individual programs, and we can tell which services they're going to use from the system. For example, when I download a piece of code that I'm going to run in my browser, I can check to see if it uses the TCP/IP stack, and if it doesn't, I know it can't send spam, for example. Okay. So the result of this experiment so far is what we call the Singularity version 1 system. Okay. It's a very microkernel-like design, which means that there's a small kernel at the bottom of the system, and then all of the services and all programs, all services, and all device drivers run in software-isolated processes outside of the kernel. Okay, so the network driver, TCP/IP stack, file system, things like that all run in separate programs. The kernel itself is written almost entirely in safe code. 95% of it is written in C#. We do have some unsafe C# code. So, for example, our garbage collector is written in C#, but it has to break the type system at points, and so there's unsafe code in it. And the good way to think of this is we have assembly code at the same place that any other operating system has assembly code, same places. So thread context switch, exception vectors, things like that have assembly code. And then we have a small amount of C++ code in the startup code. But other than that, the entire rest of most of the kernel is written in C#. One of the things I'm particularly proud of is all of our device drivers, every single device driver in the system is written in safe C#. Okay, so there's a number of properties we can verify from that. And at this point, it's a fairly complete, we'll qualify that a little bit, server-type operating system. And what I mean by that is we have no GUI whatsoever. Okay. We do have a TCP/IP stack. We have a file system. We have a web server that runs on top of it. We can run the SpecWeb 99 benchmarks and have published results about the SpecWeb 99 benchmarks. We have a wide, the other word I should clarify, so we have a wide class of device drivers. What that means is there's a whole bunch of different types of devices that we have device drivers for, but we usually only have about one of each. So for example, we have one sound driver, enough to prove out that we know how those work, but not enough to provide you a wide variety of hardware you might run on. But it's a fairly complete system in this regard. It is functional, you can use it for specific things. Okay. Singularity is a research vehicle. When we started Singularity, and as we were writing it, we had one goal in mind, and that was, the way I would describe it is, one or two researchers ought to be able to have an idea for a completely new OS abstraction, and they ought to be able to go put it into Singularity and produce a publishable result on the order of about a year's worth of time. Okay, and that was really the goal of why would you build a completely new operating system? Well, one of them was so that we could do new OS research that was a lot harder to do in existing systems. So the architecture is quite simple. And clean. The abstractions in the system are very simple. They're orthogonal. And the implementation is quite simple as well. And that makes it a very approachable system. So with this fairly complete, approachable system, there's a number of areas of ongoing research that we're doing in the Singularity project. So version 2 of the system as we evolve and try out new ideas. One of the ideas we're working on is that we actually have some publications on is a thing called compile time reflection. So this is a meta-programming system that takes place at compile time as a replacement for the CLR and Java's dynamic reflection systems. And the advantage of the compile time reflection is it's much more analyzable and it's easier to use. We've also done some work in hardware protection domains. So our SIPs are software isolated, but there's interesting ways that you can compose SIPs with virtual memory hardware. So one of them being if you're a belts and suspenders kind of person, but there's a number of other ways that you can produce very interesting systems as well. We're doing work in heterogeneous many-core processing. We're also doing work in the area of typed assembly language. So because Singularity depends on static verification on type safety, the way it currently works is we do the verification at the level of MSIL code, and then the backend compiler Bartok generates x86. And so essentially the backend compiler is part of the trusted computing base. And so the ongoing work is teaching Bartok to generate typed assembly language and then doing verification on that so we can remove the compilers from the trusted computing base. One benefit of that is it means that we can let anybody write a compiler for the system. And Chris Hoblitzel on my team in particular has done quite a bit of work on unifying the proof systems for both the typed assembly language and the runtime as well. So some ongoing work there. And finally, one of the areas where we're working in is what I call, for lack of a better word, post-PC computing. Okay? One way to describe this is, what does computing look like for the billions of people that will never own a PC? And I assert that there are billions of people that will in the world that never will own a PC. What does computing look like for them? And we think it looks like something that we call a C-phone. It's a mobile device, but it doesn't run by itself. It's connected to the cloud and uses other things like PCs as additional computing resources. And the way I'd like to describe it is, rather than the phone being a peripheral to the PC is a peripheral to the phone. Okay. So as we kind of alluded to, we are making the Singularity, the V1 code base available for academic research. We think it's a great platform for doing research. It's where we're doing our research, but we also think it's a great platform for people outside of Microsoft to do research on. And I'm going to bring up Mark and let him talk about the RDK a bit.
This thing on? Good. Hi, my name is Mark Lewin. I'm sort of your host, I guess, for this mini-core concurrency track here at the Faculty Summit today. But I'm also been working closely with Galen and Jim over the course of the last year to try to realize this goal of making Singularity available for academic consumption. As Galen said, the system is designed in a way to enable substantial and innovative work to be undertaken and to be realized in the form of a publishable result without a significant number of years of effort being invested to recreate the wheel or to have to undo things that a standard operating system has baked very deeply into its architecture. This has been a very successful model within MSR, and it's, as you've gathered from the talks with Craig Mundy's comments earlier this morning, with Burton's talking about today, and the talks you'll hear later this afternoon, there's a lot of energy going into a new era of innovation, exploration, and reevaluation of concepts that have been surfaced over the last 30, 40 years, and a lot of new, critical new thinking. We think that Singularity can be a valuable laboratory for enabling you all to experiment with new concepts, and to do that in the context of a powerful and contemporary tool chain and operating system, and get to meaningful results without having to fight against the architectural biases of larger operating systems that are out there now that historically have been what folks have used, or also have been relegated to using small toy systems that don't have the expressive capability or the fully realized implementation that Singularity has. Where we are at in this is that we have just, in the course of the last 3 months, been able to share this first version of Singularity with a couple of victims, I guess, some very, very willing people who are willing to experience things in their raw state and give us feedback on what their experience is like, and also so we can get an insight into what people outside of MSR are inclined to do in putting Singularity to a variety of uses. It is our goal to broaden availability over the course of the rest of 2007, and it is further is our goal to make it broadly and freely available early in the next year. So one of the things that I wanted to do, and I think later in the slides, Galen has my email address on one of these, on one of the slides, is to, over the course of the summit here, if and certainly over the course of the remainder of the session we have here at lunchtime, is if you have some specific interest in or a specific project that you think is a good map with the architectural goals that Galen has spelled out in his presentation here, that you find a way to contact me or Galen or contact me through email, and it's a conversation we'd like to advance. I do want to, again, make it clear that things are in a pretty basic state right now, as we're just learning what it is to create and share something like this with an external audience that doesn't have access to the oral tradition and the hallway culture that we have in MSR. But that's something that we want to a gulf we want to span, and the best way to do that is to find people who are interested in taking on that challenge and then working to make them successful, and that would be you. So the other thing that I wanted to point out in this context is that, and I think this was announced this morning, or if it's not, it's will be discussed at some point during the program, is that our group, Microsoft Research, on an annual basis has a series of requests for proposal, or RFPs. And these are solicitations for research projects, usually focusing on different problem domains, spanning from digital inclusion to bioinformatics to synthetic biology, tablet and pen-based computing, robotics, and the like. It's our intent to open up an RFP for mechanisms for safe and scalable concurrent computing. It sort of keys off of what Burton was talking about, and is certainly an excellent match with what Singularity has to offer in terms of incubating ideas and being a laboratory for innovation. So I want you to keep your eyes and ears open for that announcement. It currently is our plan to open that RFP for proposals around the time frame of the SOSP conference at the beginning of October of this year. So if I'm doing my job right, hopefully the news will find its way to you through a variety of channels between now and then. But I do want to get that on your radar as well. So that's sort of my infomercial for the RDK in here. Again, for any of you who are interested in this, talking about this in more detail, please don't hesitate to send me email or to find me during the course of the conference here, and let's discuss it in more detail. Thanks.
Thanks, Mark. So I guess I'll just summarize by saying, we think we've built a pretty good basis for doing experimenting in more dependable systems through the pervasive use of safe programming as a language, very lightweight process, and verifiable specifications around the system behavior. Again, remind you, Singularity, it's a research prototype. Again, it's not a replacement for Windows. It's where you can try out it's a place to try out new ideas. We have a website, research.microsoft.com/os/Singularity. A really good place if you don't know anything about Singularity is Gemini's operating systems review paper that was released this spring is a good summary of the research to date and also what we're doing going forward, and points to the other publications where there's more detail. And of course, here is Mark's email address if you want to get involved in the RFP or if you want access to RDK. I did want to, they're not very bright, but one of the things I should definitely acknowledge before we go any farther is the large number of people that are involved with Singularity. By my last count, we're something like an order of 40 people have touched the Singularity code base, Microsoft full-time employees, plus about 30 interns over the last year. In fact, there's a number of people from the Singularity, who contributed code to the Singularity project here. Could they all raise their hands? Yeah, there we go. Okay. So at this point, I'd like to open it up for questions and answers. Anything you want to know about Singularity or the RDK or the RFP? Yes, Mom.
I have a question about the RDK. So one of the opportunities for Singularity seems to be looking at, or could be looking at, the language support for operating systems. Along the lines of what you've done with Sing Sharp and things like that. I was wondering, will the RDK, in some eventual form, support work on the sort of compiler language side as well as on the operating system side?
Okay, so the question is, how much support do we have in the RDK for language experimentation? And the answer in the V1 RDK right now, we don't have any of the compiler sources. We have the compiler binaries, although there's a.
I'm agreeing with you.
Yeah, can we talk about Bartok?
Sure. Yes.
We are doing an RDK for Bartok, which is the back-end compiler. And we haven't yet talked about an RDK for the Sing Sharp. I would expect we'll figure out something to do at some point.
As we're working our way through the totality of the technology chain that is the Singularity project, where different pieces have, I don't want to say encumbrances, but they're owned by different people and they serve a variety of other interests, and they're at different stages of presentability. So some tools that, like the Bartok compiler, which is an essential tool for building Singularity and building applications for it, exist in the RDK as a tool, as opposed to being a research asset in its own right. And so we're working through these on a case-by-case basis. It certainly is our goal to enable exactly what you're talking about. There's still some foundational work that needs to be done, and we have to work through the pedigree of all of the stuff that's in, for example, the Sing Sharp compiler, to make sure that it's in a supportable and shareable form. I mean, as with most research projects, I think Galen would agree, sometimes things are created, not everything is created with a goal towards sharing it publicly. And not everything that's created finds being put to use in exactly the way that was expected. And so these are challenges for us as we're trying to figure out a way to realize this goal of fully enabling the space and opening up the totality of the research vision that Galen laid out in the slide. So I guess the short answer to my long-winded thing there is we're trying. But it's going to be a phased thing.
Yeah. Which I guess another thing I should comment on. So we do anticipate doing a new RDK drop every 6 to 8 months as we evolve things. So.
Right.
Next question.
So what are you guys doing on moving the OS into multi-core? Is there a natural way of looking at scheduling and stuff like that?
Okay. So the question was, what are we doing in multi-core and what does it look like? Yeah. So there's a couple of insights that we think Singularity offers some benefits from Manycore. One of them is the SIP architecture itself. So it encourages you to write fairly lightweight, isolated pieces of code that interact with other pieces of code exclusively through message passing. Okay, and so and the granularity of SIPs tends to be such that you can imagine, dedicating one or more cores to a particular SIP, taking advantage of the architecture that way. Another aspect of the architecture, in Burton's talk, he talked about, if we're going to have a lot of cores, it isn't obvious that all those cores are going to look the same. That we'll see heterogeneity both in the instruction set, but also in the implementation of those cores. And so we have done some work in Singularity. Well, we have the way binaries to get delivered to the system is as MSIL, not as native instruction set. And so that allows, there's an abstraction level at the point that you do install time, we can generate new instruction code for new instruction sets. So for example, we're working on a system where we have both x86 and ARM cores in the same system, and individual components can be compiled for one or both of those and placed dynamically on those different systems. And the programming model is exactly the same. Another thing that we've done a little bit of work on is in terms of, one of the things you see on these many core processors is they tend to have much smaller caches than we've historically seen. And so we have an idea called a subservient kernel, where we take a very small version of Singularity and run it on some of the cores. So we're not doing a symmetric operating system across all the cores, but we're spreading out different subsets of the operating system. So those are the kind of the things that we've been looking at in the many core space. But I'm sure there's many other alternative things that people could be looking at, and higher up scheduling and a bunch of other stuff that we haven't got to yet.
No shared memory abstraction you have the schedule process?
Well, so within a SIP, within a software isolated process, there is shared memory. Okay, a SIP, within the SIP, you have threads, you have shared memory. We do have a version of the STM, the software transacted memory, that you can use it, or you can use just regular you take care of yourself shared memory. And so, for example, the scheduler, well, it has shared memory within itself, but across processors, or across SIPs, there is no shared memory. Another question?
Another question I asked about applications. So it's often difficult to do systems research for applications. And one of the big benefits of something like Linux or Windows is there are a million programs out there you can run with. There are standard benchmarks. You can publish results like the people believe you should. So I was wondering, if I was to adopt Singularity, what are some of the prospects for interesting big applications that sort of stress the system?
Well, we don't have any of those extraneous programs. We only have the really important ones. So the answer to that is the set of applications is very, very small right now. And it's one of the places where we're trying to put some investment in and add in additional applications. Right now, basically, we have web server, we have SpecWeb 99 benchmark on the system. We have the Bartok compiler will run on top of Singularity, so that's what our benchmarks have looked like so far. We have, anyway, it's if there was one place where I'd say is the Achilles heel of Singularity right now, it's definitely the lack of applications. But we're working on that.
Does it support any? What is the prospect for porting applications? Does it support any standard libraries that would make it easier to port applications, C# applications?
Right. So we have quite a few of the CLR type libraries on top of the system. The way you should think about porting code to Singularity from, say, the CLR is that it's very analogous to porting code from one version of Unix to the other. Okay. In other words, if you have if it's pure computation code, it's just pick it up and drop it over. If you're getting down in the bowels of the system and touching a bunch of things, it's much, much harder. The place where we've actually seen have the biggest problem is we don't support dynamic reflection. The full dynamic reflection in the CLR. We have a subset of it, a very constrained subset. And that's the place where we typically find if you go pick random CLR code base and try to bring it into Singularity, the most likely problem you'll have is that it's using someplace in it dynamic reflection, and you've got to replace that with the compile time reflection. So your mileage may vary, I guess, is the answer. You know, and we haven't talked a lot about this in the academic community. Within Microsoft, I get questions like this all the time with people, and my answer is always, get the code, look at it, and see if it works for what you're trying to do, your piece of research. And you know, there's going to be definitely lots of research that Singularity is not the appropriate platform for, you know, that we don't have a particular benchmark you need or something like that. And my suggestion is, you know, get the code and look at it and find out. And if you need to go someplace else, go someplace else. But if Singularity is a good platform for you, fantastic. We're also one of the reasons for kind of gradually rolling out the RDK program has been so that we could kind of explore, well, where should Microsoft be putting investments so that the academic community can better benefit from Singularity.
Right. And I should add to that, too, that it is our goal to foster community around Singularity. So it's not that we don't see this as being, just a one-to-many relationship. Ideally, this is a many-to-many relationship. And to the extent that we're clever in figuring out a way to foster community, to foster lateral sharing, so to make it so as people on the fly create assets that would be useful to other people doing Singularity-based work, you know, we want to do what we can to make sure that either there's a hub for that stuff, or at least there's a virtual route where we can start from, where people can quickly locate that stuff and put it to best use. But and we understand that we're starting from a fairly basic position here, but we have a very strong asset to build around, and that we're hoping the diversity of interests that people pursue with Singularity will be one of the largest drivers for getting an interesting variety of application level code and benchmarks and tests up. But we're still obviously very early days here.
Yes, you could ask a follow-up question, Mike.
So, the thing most people do for research systems is put the POSIX interface on top of it, even if they don't want to, so they can run processes. Like Monken this, Windows, Pages this, Ruby does this. Is this technically feasible to put a POSIX-related interface on top, or is it sort of philosophically do you do it? Your goal is to get that, and you're going to hack the license if we do that?
You could do it, but I'd come hate you, huh? No, the answer is technically it's feasible. I talked about the hardware protection domains that we've put into the system where you can, we have software isolated processes, that's our ideal, but we also have this mechanism where you can isolate a process using hardware protection. And someone could very conceivably implement something like POSIX in a POSIX subsystem in a hardware protection domain. And I'd actually love to see somebody do something like that. Okay. Yes?
So as a sort of policy issue, let's say this isn't my area at all. I mean, what if some energetic young programmer created a windowing system for it and said, well, Linux came from Minix, why don't I take this wonderful starting point and make something that really can be used by people in the real world? And they started to do that and generate some code and so on. What would you do with that?
In what way are you asking that question?
Well,
would I jump up and down with joy? Yes, I would.
And Microsoft would support that kind of thing?
Well, okay.
Support's a tricky word.
Yeah. So,
would anyone say don't do that? I don't think we would say don't do that.
Okay.
Let's say someone came up with some really neat code that added to it. Could that code be added to the code base so that in your subsequent distributions it would be there? So
the short answer is we don't know. We don't know how to deal with this yet, and this is one of the things we're trying to work out. So, the way we've structured the license right now, and it is an NDA license right now in the RDK, primarily so we can just keep track of what's happening. But anyone who has a license can share code with anyone else in the license. And so this easy answer right now is, well, you could share that. If someone did that, they could share the code available with as many people as possible. One of the things we've thought about, not very deeply, so we don't know how it's going to work yet, is a way of having a shared repository out on the web in what is our version of not SourceForge, but
right,
CodePlex.
Thank you.
For example, you can imagine there being, for example, a pure Microsoft distribution, which has, we indemnify it and everything else, a distro, and then a broader distro, which is here's code that everybody else has thrown in, and your mileage may vary.
Right.
And we're, it's something we're learning. We've never attempted something like this at Microsoft. But on the same hand, we had never attempted a cross-group research project like Singularity before we did it either. And so we're one for one. We're feeling quite optimistic that we can do some great things here.
Right. Just from the licensing landscape, as Galen said, we're learning a lot of stuff. I mean, there's some things that, regardless of our ambitions, we exist in the cultural norms of Microsoft too. And some of those things are relating to the fact that this is, while this is, as Galen said, purely a research project and is not posturing to be the next version of Windows or a commercial product, the model of Microsoft Research is to draw attention, is to provide a pipeline of ideas to the rest of the company, amongst other things, including publication and generally advancing the state of the art. There is some importance that we place on trying to make sure that for the code that we work on internally, that we know where it comes from, we know what its IP story is, we know what its patent story is, and we can. It's sort of like doing the static verification. Once you have a lot of those things taken care of, you can proceed with a certain level of confidence that you don't have to keep checking those things over and over again. So on the take-back story, in terms of someone who wants to make a contribution, probably the thing that would happen in that case, and again, we have no mechanism for this right now, is that you'd have to do something like a pedigree check and work through the code contribution so that we then absolutely understood fully its licensing story. And I'm speaking not specifically about Singularity, but this is a general predisposition Microsoft has in terms of how it works with any code that's generated outside the company. And it's a cultural bedrock, and it's just something we have to find out if there's a make sense way for us to do that, or if we find a halfway scenario like Galen was talking about, where we're able to support and provide sustenance to an external community, and we can observe it. But the process by which innovation might flow back into Singularity or Microsoft is when more reading the paper or doing some other thing that doesn't involve directly incorporating code back in. But again, this is a learning experience for us, and a pretty unique one, and we're pretty excited about the possibilities. We look at these things as opportunities, not as problems.
And I would say, I think we're pretty open-minded. If you've got ideas of how these things might work, this is definitely something we're looking at from the academic community. Is what can we do to make the process itself work better for people?
Right. One good thing on this is that it is purely a research project, and control of that project is held pretty closely by the Singularity group. So there's a lot of creative flexibility that goes into that. It's not like you can come up with a good idea and someone says, well, we're backlogged 5 years with good ideas, so we can't even begin to come up and look at your thing because we already know what we're doing until the year 2013. With the Singularity group, I mean, it's much more of, I think, of an idea meritocracy. Certainly there's an agenda that the researchers in the group have laid out for themselves, but there's also a lot of flexibility within that agenda to make Singularity what they want it to be. And I think that how that plays out in terms of flexibility, in terms of reacting to good ideas or opinions or feedback, again, remains to be seen as we go public for the first time. But again, I'm optimistic and view it as an opportunity and not at all as a problem.
Got time for one or two more questions? Anybody's got one? Tom?
How big is the code base?
How big is the code base? Roughly somewhere between 200 and 300,000 lines of code when you take into the operating system, all the device drivers, and everything that runs on top of it right now.
Yeah. There was a lot of empty space on the CD-ROM that I sent to people.
That's filled up with very boring videos of Jim and I.
Yeah. I should say also, by way of explaining where we're going with the RDK, the RDK is going to continue to grow on the technical track that Galen's laid out, and based on the feedback that we gain from you all as you take your first steps into applying it towards your research goals. We also are intent on supplementing it, supplementing the core technology over time with information on how to learn what it is, how to use it, how to build it, how to modify it. A lot of that will take the form of video, because it's a nice high bandwidth way to make talks like this and more detailed architectural talks available to a wide audience when we can't bring everyone together. And There are also engineering groups within Microsoft, within my team, ER&P, that will be making investments in supplementing the core technology and Singularity with specific features to abet particular kinds of research. One of those areas will likely be in the area of sustainable computing, where we'll be working to augment the core Singularity with interfaces to allow you to understand the patterns of energy consumption within the system, instrument that, learn about that, and ultimately be able to implement algorithms and policies that might, as Burton was talking about, allow you to express what trade-offs you want to make in terms of computational throughput and overall energy consumption in the system. Again, those kinds of investments will be opportunistic, and the RDK will be a vehicle for that. And that internal to Microsoft, that'll be a way that we look at the challenge of also folding technology back in, minus the IP problems. But as the Singularity community grows to encompass other groups within MSR and possibly other groups within Microsoft, we see a lot of vitality there. And the periodic refreshes of the RDK hopefully will be a way to get that incremental innovation and contribution to you as soon as possible.
There was a question, second back. Yes.
Which verification tools are you using?
We have a bunch of homegrown stuff. Somebody's putting, let's see, chess. Somebody's doing some work with chess right now. Chris, what is the... Yeah, Boogie, Spec Sharp. So, and a bunch of just ad hoc tools that we build as well. Okay.
Well, should we wrap up?
Well,
go ahead, I'm going to choke.
Anyway, thanks for your attention. Again, if you have later on questions, send mail to Mark or me. Thank you very much.
Right. And again, I want to encourage, I'm sorry, for Galen. I want to encourage you as you head out to pick up this paper, research, Rethinking the Software Stack. This is the OSR paper that Galen was talking about. They're on chairs there by both doors. Please go ahead and grab a copy. If there's a colleague that you think might be interested in one as well, grab it. It's also available, I think, on the Singularity site there as well, downloadable PDF. Galen's and my homepage both have links to it as well. So, thank you.